Hi everyone, thank you for being here today. My name is Wen, and I'm joined by my group mates Qing Jianxi, Yihen Yao, and Grayson Gong. We're excited to share our project, Andrewware, a malware detection using machine learning techniques. Let me ask you a quick question. How many times do you use your smartphone in a day? Smartphones are a big part of our lives, whether it's for banking, shopping, health tracking, or work. But with this convenience comes risk. Malware and the virus can attack your device, stealing data, recording what you type, or even gaining access to sensitive information. This not only puts your personal information at risk, but can also slow down your phone and leave you open to hacking. Android is the most widely using mobile operation system, but it's also a big target for cyber criminals. Unlike iOS, Android's open system allows developers more freedom to create apps. Well, this is great for innovation. It also makes it easier to malicious apps to snack in. These apps can steal personal data, damage your device performance, or even cause major security issues. Traditional antivirus software often looks for knowing patterns or signatures to find the malware, but cyber criminals are smart. They create new types of malware that signature-based methods can't detect fast enough. This is where machine learning comes in. In our project, we test machine learning algorithms like random forest neural network and convolutional neural network to detect malware. Instead of rely on knowing patterns, these models learn to recognize unusual behaviors like strange permission requests or suspicious network activity. This dynamic approach is more effective at catching new unknown threats. Our goal is to create a system that can quickly and accurately identify malicious apps, protecting users like us from cyber attacks. To do this, we analyze data, features, and relationships to training our models. In this presentation, we will guide you through our process, starting with the dataset, move on to the data models we built, and finally share the results of our work.
Traditional signature-based techniques often fail against new malware strains, but research shows that the machine learning models like the random forest, SVM, and the neural networks can effectively identify malware by recognizing behavior patterns. Studies including Liu and L emphasize the importance of the feature engineering in enhancing detection accuracy, highlighting ML's potential in strengthening mobile security. We used a dataset from Kaggle called Android Mobile Detection. It has approximately 356,000 records across the 88 columns. Some key features in the dataset include flow ID, source IP, destination port, protocol, total forwards packets. The raw data was highly imbalanced, with only 6.7% benign samples, but 93.3% malicious samples. This imbalance makes our machine learning analysis more challenging, because models may become biased towards the majority class and lead to poor detection of the minority class. The dataset categorizes software into 4 classes. The first one is the benign, harmless software. The second one is adware. Software can display advertisements, disrupt user experience. The third one is SMS malware, involves sending unauthorized MLS messages and could lead to financial losses for the victim. The last one is a scareware, designed to frighten users into taking specific actions and often involves fake alerts. To better understand relationships within the data, we computed correlation between features using Python's core function. This helps us identify some useful features. Independent features like source port and source IP are uncorrelated with others, so they are valuable for classification. Features moderately correlated with the label provided insight into potential predictive attributes. During the feature engineering, we decomposed the flow ID into components like source and destination IPs and ports. We broke down IPs into their 4 8-bit octets, which hold distinct network significance. For example, the first octet represents the network class A, B, or C, revealing the scale and the nature of networks involved. IP addresses are typically stored as strings. We broke them down into their individual octets. Each segment of an IP address holds a specific meaning. We extracted key features from the flow ID field, including the source IP, source port, destination IP, and destination port. To enhance the granularity of our analysis, IPv4 addresses were decomposed into their constituent 8-bit octets, divided into 4 parts, each with specific network addressing significance. The first octet represents the network class of the device, where classes A, B, C denote ISP, company, or private networks respectively. The second octet facilitates subnetwork segmentation, enabling hierarchical network design by dividing network into smaller, manageable groups. The third octet allows finer subdivisions within subnets, organizing devices by departments, buildings, or geographical locations. Finally, the fourth octet identifies individual devices within a subnet, such as a host ID in an address like 192.168.1.1. Class distribution includes Class A 0 to 127 for large-scale networks, Class B from 128 to 191 for medium-sized networks like universities, and Class C 192 to 223 for small networks. This level of details help us understand malicious behavior better. Moreover, features like minimum and maximum flow inter-arrival times can indicate if a device is communicating in a pattern that looks like a human-driven or machine-driven. Malware often just generates the burst of the traffic at unusual intervals, so identifying these timing patterns is crucial. Visualizations like stacked bar charts demonstrated the frequency of the malware occurrence across these networks classes, uncovering trends in malicious activity. We also classify dataset features into three types: numerical, categorical, and useless. Using a combination of the thresholds and the logical checks, numerical features such as the flow duration and the packet length mean describe the measurable properties of the network flows, while categorical ones like protocol define specific identifiers. Redundant features like source IP were marked as useless. Using histograms, we evaluated each feature's distribution to ensure meaningful classification. For example, categorical features had fewer unique values, making them discrete, while numerical ones exhibited continuous variation.
Entropy and Gini impurity are two fundamental metrics we use in decision tree algorithm in order to evaluate the quality of splits during feature selection. Entropy represents a level of uncertainty or disorder within a dataset, and a value of 0 indicates a pure node, where all samples belong to the same class, while higher values indicate more class diversity. Entropy is calculated as the sum of negative products of class probabilities and their base 2 algorithms, reflecting the degree of randomness or unpredictability in the data distribution. And for Gini impurity, on the other hand, we measure the probability of misclassifying a randomly selected sample from a node if it was labeled according to node's class distribution. And like entropy, a Gini impurity value of 0 denotes a pure node, while higher values suggest more mixed classes. Calculated as 1 minus the sum of squared class probability, Gini impurity provides an intuitive measure of node purity, and both metrics guide decision trees in identifying the optimal splits by reducing impurity, and Gini being more computationally simpler and slightly faster. The random forest classifier leverages decision trees guided by matrices like Gini impurity and entropy to perform feature extraction by assessing importance of each feature in splitting the data. In the ensemble method, multiple decision trees are trained on different subsets of the dataset and features, introducing variability and reducing overfitting. During the tree construction, Gini or entropy is used to determine the optimal splits at each node, ensuring that features contributing to the most to the class separation are prioritized. And the cumulative contribution of a feature across all trees in forest is then aggregated, yielding an important score, and this score reflects how effectively a feature reduces impurity or uncertainty and helps us to identify the most influential attributes for our classification. And from this, forward average bias bulk reveals patterns in bulk data transmission, while flow ID captures traffic patterns unique to malicious activity. Source port reflects specific malware communication behaviors, and flow IAT minimum identifies timing patterns indicative of malware, and source IP points to malicious IP subnets. These features fall into three categories: data transmission patterns, communication metadata, and source identifiers. And the k-means clustering algorithm provided instrumental in analyzing the numerical features of the dataset, which were meticulously normalized using standard scaler to ensure a uniform scale across variables. And this essential pre-processing step can adjust all features to have a mean of 0 and a standard deviation of 1, which can enhance the algorithm's ability to accurately group the data. And initially, the clustering was configured to identify 4 distinct groups, yielding a silhouette score of 0.1465 and a Kaliski-Harab's score of over 40,000. And while 3 scores, and these scores indicated moderate clustering quality with some overlap among clusters, and the highly meaningful patterns within the data. And to visualize these groupings, PCA were employed to reduce the dataset's dimensions and project it onto a two-dimensional plane, offering a clearer view of the underlying structure.
Random forest operates as a ensemble of decision trees, combining the outputs to improve robustness and generalization. By averaging the predictions in a regression by taking a majority vote in classification, random forest reduces overfitting while maintaining high accuracy. It excels in handling large datasets with high dimensional features. Support vector machines focus on finding hyperplanes that best separate classes in the feature space. SVM uses kernel functions to transform nonlinear data into a higher dimensional space where it becomes linearly separable. Gradient boosting and ADA boost are ensemble methods that sequentially improve weak learners, often simple models like decision trees. Each iteration focuses on correcting the errors made by the previous model, resulting in progressively stronger performance. Artificial neural networks, or neural network, is a computational model inspired by the structure of the human brain. It consists of layers of interconnected neurons that process input data and progressively transforms it into meaningful outputs. The input layer receives the features of the dataset, while the output layer generates predictions. Between these two, hidden layers perform the core work of feature extraction and pattern recognition. Each neuron in the layer connects to every neuron in the next layer through weights which are adjusted during training. Mathematically, the flow of the data involves linear transformations and nonlinear activations. For example, an input that is multiplied by a weight matrix and shifted by a bias vector forms a linear combination. This result is passed through an activation function like ReLU, accumulating in a final layer where a function such as softmax converts the output into probabilities of each classification. The network learns by minimizing a loss function, which is cross-entropy loss in this case, which measures the difference between predicted and true outputs using optimizers like Atom. We use the Atom optimizer in our network, and the network iteratively updates weights to improve its predictions. Neural networks excel at capturing relationships in the data, making them versatile for tasks like image recognition, speech processing, and tabular data analysis. In this case, we are trying to predict whether or not an app is malicious or not using the tabular data. Convolutional neural networks are a specialized neural network designed to handle spatial data, such as images or sequential data like audio signals. Unlike traditional neural networks, which rely on fully connected layers, convolutional neural networks use convolutional layers to capture patterns of local regions in the data. These layers apply filters or kernels that slide over the input, detecting features like edges or in images or trends in sequential data. The results of these convolutions are feature maps, which highlight the presence of specific patterns. A convolutional neural network typically involves convolutional layers using pooling layers, which reduces the spatial dimensions of the data. Pooling retains most of the significant features of the data while reducing computation and the likelihood of overfitting. After the convolution and the pooling layers, the features are flattened and mapped to a one-dimensional vector and passed through fully connected layers for classification. For regularization, techniques like dropout are applied to randomly disable some neurons, preventing over-reliance on specific features. Convolutional neural networks are optimized using the same principles as the traditional neural networks, employing a loss function and an optimizer. In this case, we are using the columns or the features of the data as a sequential list and then performing convolutions on this list. This results in a image-like or vector-like data representation, and therefore we can apply convolutional neural networks to this task. We compared our results to Ocon-Ulu's Kaggle solution for Android malware detection. Our random forest model reached an accuracy of 0.83, which is 2% better than Ulu's result, and our bagging classifier performed even better with an accuracy of 0.85. This improvement comes from the advanced feature engineering and optimized algorithms. By carefully selecting and refining features like data transmission patterns, timing differences, and communication details, our model could better identify the differences between malicious and safe behaviors compared to Ulu's approach.
A deeper look into the results reveals why ensemble methods like random forest and bagging classifier outperform other models. Ensemble methods combine predictions from multiple learners, which mitigates the risk of overfitting and biases that individual models often face. For example, random forest aggregates results from numerous decision trees trained on different subsets of the data, which enhances its ability to generalize across a wide range of malware types. And bagging classifier builds on this principle by creating independent models and averaging their predictions, and further reducing the variance. And these ensemble approaches inherently capitalize on diversity within the training process, making them particularly resilient in identifying malware that exhibits varying patterns of behavior. So in contrast, simpler algorithms like logistic regression and decision tree lack this robustness as they rely on more rigid assumptions about the data.
The results have highlight the challenges and the potential of the neural network models like FNS and CNS. While these models have shown strong theoretical performance in pattern recognition, their application here is constrained by the size and the complexity of the dataset. Neural networks, especially convolutional architectures like CNNs, excel in tasks with special data like images or high-dimensional data where intricate patterns exist. So, however, for this specific task, the relatively limited size of the dataset and the absence of rich spatial correlations made it harder for these models to outperform simpler, well-tuned classifiers. Additionally, neural networks are highly sensitive to hyperparameter choices, and their training requires significant computational resource to fine-tune effectively. As a result, while CNNs achieved a respectable accuracy of 0.7, their performance was outclassed by the ensemble methods that could better leverage engineered features.
Feature engineering proved to be the most significant differentiator between our approach and Ulu's baseline models. By identifying and incorporating features such as bulk data transfer and IPv4 extraction, we were able to significantly enhance the information fed into the models. For instance, features that emphasize timing patterns such as flow IET capture malware's unique communication timing, while source IP and its 4 octets help pinpoint malicious subnets. These nuanced features directly contribute to better classification outcomes as they align with the behavioral patterns malware exhibits in real-world settings. In contrast, a lack of these tailored features in Ulu's implementation likely restricted the capability of his models to generalize effectively. The 2% improvement in random forest accuracy, along with the gains in other models, underscore the critical role that feature engineering and model optimization play in improving performance. Our approach demonstrates that even with small adjustments, such as introducing domain-specific features or optimizing hyperparameters in ensemble methods, can yield significant results. Moreover, the consistency in our model's precision, recall F1 scores, reflect their ability to maintain a balance between identifying true malware and minimizing false detections. This balance is essential in practical malware detection systems, where both false positives and false negatives carry substantial costs. Thank you very much.